to the cloud. Okay, so hopefully you guys all got enough sleep and you weren't up too late last night finishing the homework and quizzes. That's one thing I know about due on Sunday is it makes Monday morning a little hard if you have to spend a lot of time on it late at night. But yeah, you know, life. Okay, so today, you'll notice after class, I don't even check my lab today yet. 11.4 is up, and honestly, 11.4 is it's really short. I wanted you to do one of those problems where you find the equation of the tangent line, and then so that one, remember, you use the instantaneous rate of change to find the slope, and then that point that you found during that process to find the equation. And then there's some on there about finding the derivative at certain points. So the way the problems are worded in there, I wanted to kind of go over that. So for example, they'll give you a function. I don't know, just probably like a squared function, x squared plus 4x or something like this. And what it asks for is maybe something like this, maybe the derivative at 2, but it doesn't, and I know we're getting used to the derivative notation, so that's the thing I want to make sure we understand, is when it asks for something like this, make sure that you just know, okay, that's the derivative evaluated at 2. So you would go through, you could find the derivative of this problem using that definition that we did last time. And then once you get that, remember that's going to have an x in it. You put the 2 in for the x. And I think it might even ask for more than that. So it might ask for this one. There are some, I think there's at least one where it just asks for the derivative in general at any x. So both of these, you're going to use that derivative definition that we learned last time. It's just on this one, you're going to take it one step further and put a 2 in for the x and get a value. On this one, there'll be an x in your answer and you'll just leave it like that. But that's the way they word those problems. But no, like I said, it's a really short one. I don't want you guys to have to spend too much time continuing to like do the instantaneous rate of change on the tangent line slope one. And honestly, today we're going to learn really easy ways to find the derivative, which should be good news because I know last time we had to do a lot of work to find the derivative, where we took our IROC calculation where there was an a before, which was a number, and we replaced it with x. So I am going to write the derivative definition down for you again. Remember, the more you write it, the more you remember it. So when you do have to use it, I want to make sure that you know what to do. And remember, it just looks a lot like the instantaneous rate of change with one difference. So instead of f of a plus h, remember, we just replaced it with f of x plus h and f of x. And it was like this. And remember, having that x in there instead of just a number for a made our calculations a little bit tougher. We had to carry over more terms. Things didn't cancel out as much or combine. So most of your expressions had more terms than before. But remember, what we got at the end was really helpful because we could put any value in there and find the derivative at these certain points. Okay, so again, just make sure you have that written down. You'll have to use it on your homework, possibly. I say possibly because I am about to teach you faster ways of taking the derivative. Now, does that mean I don't care about this anymore? Absolutely not. I care very much about this, and I care very much that you know how to use it. This is the long way to take the derivative. And on your homework, guys, when you're looking for the derivative, I don't know if you use the long way or the short way. I'm going to say in 11.4, I'd like you to use the long way. I'd like you to use this. But after you learn the short way today, you might just do it the other way for time's sake, and I can't really stop that. What I will say is, while I don't see your work on your homework or even on a quiz, I do see your work on an exam. So in our first test, there's going to be a question, and I'm going to ask for the derivative using the definition. So when I say that, this is what I mean, the long drawn out way. So on that exam, you were going to have to show me that you know it. So you might as well, on these short number of problems in 11.4, make sure you do know it, you know? What I like to do is when I do have to work out a problem using the definition, usually I'll find the derivative this way, but then I'll also work it out the short way. You guys are gonna love the short way. I'll work it out both ways and just make sure my answer matches up, because there's a lot more chance for mistake in this one, definitely. But before I erase this, all I'm saying here is this is gonna seem obsolete after our lesson today, but it is not, and you are gonna see it again, and I am gonna need your work showing me that you know it. So just keep that in mind when you're doing derivatives. Now, it is good news that that is going to become obsolete. While I say obsolete, obviously it's always true. You can always find the derivative using this. No matter what function you're looking at, that's always going to work. But what we're going to learn today are some techniques that help us find derivatives faster, like a lot faster. So this is 11.5. We're going to find derivative techniques. You guys, if we had to use the definition for derivative every time we found a derivative, we would never get anything done. So it's really good that these techniques were proven, so we can use them. So the first one I want to talk about is, let's talk about the derivative of a constant. When I say constant, remember I'm talking about just a plain number, 1, 2, 3, 4, 5, no variables involved, just a constant. So think about that in terms of being a function, like we did with the limit. Remember, we had the constant function, we took the limit of that. So let's talk about the derivative of a constant. So for my example, let's use f of x equals, we'll go ahead and just use k. This could be any constant number. So k is just a number. Notice that my function is f of x. So if this was changing in any way, there would be an x over here somewhere. So I'm going to draw it first. Just a little picture. You don't have to necessarily copy this down, but let's say on your coordinate plane, this is the value where y equals k. So your output equals k. This function is just that horizontal line where y always equals k. So while we're thinking about what a derivative means, remember this is a measure of change. We like to say it's also slope of the tangent line for the function at any point, right? So slope, measure of change, whatever you want to think about. How is this function changing from one point to another? Well, it's not, right? It's constant. It doesn't change. So I have an idea in mind what I think the derivative of a constant function would be, but let's go ahead and work it out with our definition and see if that's the case. So I haven't taught you any techniques yet. So all we have is the definition. Don't worry, this is going to be a quick one. So I have the limit as h approaches 0 of f of x plus h minus f of x over h. So I know that constant functions, even though they're supposed to be really simple, they can be a little confusing to work with because we want to change this. We want to put something in for x and get something different, even though that never actually happens, right? So I don't need side work to find f of x plus h, because if you take x plus h and put it into your original constant function, know that your value that you get out is just going to be k, because that never changes. You can put whatever you want in here, and your answer is always going to be k. So f of x plus h is k. F of x, obviously, is also k. Now you might think, well, crap, we don't have any h's up here, so how can we get rid of that h on the bottom? It's not even going to matter, guys, because what's k minus k? Isn't that just 0? So I'm taking the limit of 0. You guys, the h goes away because 0 over h is otherwise known as 0. So what's the limit of 0 as anything approaches anything? It's just 0, guys. This fact right here zeroes out the entire problem. So my answer for the derivative of this constant function equals 0. And that should make a lot of sense. Any number you put in there, if you want to take the derivative using the definition, they're going to cancel each other out right here on top. So the derivative of a constant is 0. That makes sense because derivative is a measure of change. This function is not changing. So it would make sense that the derivative of that function is 0. So derivative of a constant, always 0. So that's one technique that we can use instead of having to do the definition on a constant function. So that's one thing that's going to save us some time. So we don't deal in a lot of constant functions though, do we? I mean, we actually look at functions with x's in them. So the next technique is really going to be the one, you guys. It's going to be the one that we use all the time. When we start moving from a constant function and moving the degree up, so we're actually going to get x's in our problem, the best rule we have is called the power rule. And you guys, taking the definition on a constant function and showing you why that is what it is real simple. On this one, what we find is an emerging pattern. So to show you why this works would take a little bit longer if I was trying to show you a pattern using the definition over and over. So what I'm going to do is I'm going to give you the rule. And if you're concerned that you don't believe it or something like that, then I can always help, derive it for you. But I would assume that you're probably good with it, just giving you the rule. So if you have a function, f of x equals x to the n, any power. So this is a power rule because it takes care of any function of x raised to any power. And you guys, we have this a lot, right? We have x squared, we have, well, mainly x squared right now, but we could have x raised to any power. And if I'm taking the derivative of this function, it's actually really easy, and it does follow a pattern. What's going to happen when I take the derivative is two things. First thing that I'm going to see is whatever this power is up here, it's actually going to come out in front of my x term. So think about bringing the power down in front. So now I have nx. But you guys, there's still going to be a power here, but that power is going to change. And I think I mentioned the other day, when you take the derivative of a function, the degree goes down 1. So basically, if you started with an x squared function, you take the derivative, your answer is going to be an x to the first function. So what do you think is going to happen here? Whatever this n value is, my new power is going to be n minus 1. So guys, this is like your bread and butter for this semester. This is what you're going to use over and over and over again. The power rule, to take the derivative of x to the n, we get n times x to the n minus 1. Let's look at a quick example. because with the n's and the n minus ones in there, it can be a little bit confusing. But once you see it in practice, it's gonna be really easy to remember. So let's say I have a function, f of x equals x cubed. But I want to take the derivative. So according to my power rule, what I do is this is that n value, this is the power on x. It's going to come down in the front. So I do that. So I get 3x, and then the power on x also has to change. So this power is gone. It already came down in the front. I have to find a new power to go here, and it's going to be 3 minus 1. So 3 minus 1, I get 3x squared. So you bring a power down, you take 1 off. All right, my function is x to the 7th. Let's find the derivative. So 7 is your n value. That's the power you start with. That comes down in front. Here, it's going to change from a 7 to a 6. And that's it, guys. If you did the definition on this, you would get this same answer. If you did the definition here, which would be horrible, guys, to do x to the 7th with the definition, you would have that x plus h to the 7th term that you would have to FOIL 7 times or use binomial expansion. But anyway, it's horrible, guys. Super tedious. Now I just did it in 2 seconds. And like I said, you can take my word for it that these are the answers you would have gotten if you did use the definition. All right, so let's look at another example. This one, I have f of x equals x to the -1 power. So that's different, right? -1 is not usually a power we see, but it is a power. And guys, the power rule applies to all powers. So we can use the rule. We just have to be careful. When you're in the negatives, doing the n minus 1, you really have to be careful. So if my power is -1 to begin with, that's going to come down in front. So I'm going to have -1x. You guys take your power and take away 1 from it. So -1 minus 1. Now this is going to be -2. So be careful there. When we're counting, like say if this was -3, it's really hard not to call that -2 because 3 minus 1 is 2. But just remember you're in the negatives. So when you subtract 1, the actual number here goes up, right? So now that we know negative powers work too, let's check this one out. I have this. You guys, the only rule I have, other than using the definition, is the power rule. It only applies to x raised to a power. That's not what this looks like exactly. You guys notice I have a ratio here. I have 1 over x raised to a power. You cannot do something on top and something on bottom here. You guys, what you're going to do in this case, because it looks weird, you're going to recognize that you could rewrite that. Anytime you have x, oh, I'm not ready for that. I'm just rewriting. This is still the original. Anytime you have x on the bottom of something, how can I move it up? Make the power negative, right? What does a negative power do? It brings your value across a fraction bar. So x to the -1, I could have seen that written as 1 over x to the first, right? So I could rewrite this derivative if I wanted to, putting this term on the bottom, which would make the power x squared. That's an alternate way to write this. You have to be able to seamlessly move back and forth between negative exponents and fractions, because a lot of times you're going to be given this. You have to be able to know what to rewrite it as. So instead of 1 over x to the 4th, I'm just going to rewrite it as x to the -4th. The reason I'm rewriting it is so I can use the power rule. Like I said, from here, it's very tempting. You say, oh, wait, I know how to take the derivative of a constant. It's just 0, right? And then I know how to do this, and you're going to try to get 0 over 4x cubed, and it's not going to be the correct answer. So when you have something in a ratio form, if you can rewrite it to make it fit into our power rule, do that. Sometimes we can't, and then right now we don't know enough to calculate that, but this one we absolutely can. So I have x to the negative 4th. Now I can take the derivative of that using the power rule, so the negative 4 is going to come down in front. The negative 4 is going to turn into a negative 5, right? Because I'm subtracting 1. So then this would be my answer here. So yeah, you might have some that are written as a fraction, trying to maybe throw you off, but you know, first rule of power rule is to make your function look like something that you can apply it to. What about this? What if my function f of x is equal to the square root of x? Now, when you look at this, it doesn't look like x raised to a power, right? It looks like the opposite thing. It looks like a root, which it absolutely is. But you guys, I think I can rewrite this as x raised to a power, and I think I can use the power rule on it. Does anybody know how to do that? How to rewrite a root as a fraction? Well, it's a thing. It happens. Guys, let me show you over to the side. You've learned it somewhere along your math journey. It just might have been a while. So I've got the square root of x. So I'm going to put the little 2 out there. Remember, we never put the little 2 out here. We just know that this one is square root. And if it's anything other than square root, then we would notate it. But you couldn't have the little 2 out there. Now on the inside, this is just x to the first, right? That's true. I can rewrite this as x to the 1/2 power. Reason being is because as you switch from one to another, the inside number goes on top of the fraction. The outside number goes on the bottom. So I could do the 4th root of x cubed. If you wanted to rewrite this as a power, the inside number goes on top, the outside number goes on the bottom. You could also go the other direction too. If you ever wanted to turn the power into a root, you could always just go the other way. But this is something that you have to get used to if you're not. We use it a lot, like a lot. So know how to write your roots as powers. So in this problem, this is just square root of x. So before I take the derivative, I am going to rewrite this as x to the 1/2. Because guys, I can't use power rule unless I just have x raised to a power, which I do now. So let's use the power rule. So the 1/2 is the power. That's going to come down in front. So I have 1/2 x. And then I need to find the new power. So I have to take 1/2, and you still subtract a whole 1. No matter what this power is, you subtract a whole 1. So think about it, guys. You have 1/2, and I need to subtract 1. But instead of 1, I'm going to think about it as 2/2. So 1/2 minus 2/2 leaves us with negative 1/2. So my new power is negative 1/2. And there is your derivative. So fraction powers, negative powers, regular, normal, positive, whole numbered powers, we can do it all with the power rule. But you guys, and you know, the drawback is how many of our functions are just x raised to a power? A lot of times they have a coefficient on them too. So let's learn how to deal with that. sometimes we just have x squared, but a lot of times we have 3x squared or 2x squared or negative 7x squared. And we need to learn how to deal with that number. So if your function f of x, we're going to use that k again just because it stands for any regular old number. So I notice this is a coefficient times x raised to a power. So for example, it could be 3x squared or 7x to the 5th or something like that. And I want to take the derivative. Now, I already know how to, sorry, I have to sneeze. Okay, it's gone. So anyway, you know how to take the derivative of x raised to a power. So let's start there. Let's leave a space and let's just deal with this first because I know how to deal with that. I bring the power out in front, and then the power here gets dropped down 1. What's happening with the k is the question. And you might think, hey, didn't we already talk about the derivative of a constant? Isn't it just 0? So because this k is here, should this just be a 0? Well, that's only if the constant is actually a constant, which means it's by itself. This is not a constant anymore. It is part of a power term. So this k, it's actually really easy, guys. It just comes down. Notice I didn't take a derivative or anything. I just brought the k down. And then I went about my business and did the power rule. So let me show you an example. But yeah, that is one thing. When you see a regular number, you have to know, is this a constant in this situation? Is it going to go to 0 when I take the derivative? Or is it a coefficient? Because if it is a coefficient, it's not just going to turn into 0. So let me show you an example. So I've got f of x equals 4x to the 5th. So you can see here's the coefficient, here's the x to the 5th. And according to my rule, if I have a coefficient, it really just comes down. It just comes down into the derivative as is. So let's do that. We're going to bring the 4 straight down. It just comes with. And then we're going to do the power rule. So the power rule says I have to take this 5 and put it out in front. So you might wonder, what do I do with these two? You just multiply them together. So this is just going to be 4 times 5 out here. This x is going to be raised to the 4th power now because you take 1 away. And then definitely multiply those together, guys. You're going to get 20x to the 4th as your derivative. So what I want to do with you next is talk about functions with more than one term. Because obviously our functions don't just have one term most of the time, right? They have multiple terms, maybe added or subtracted from each other. This is probably the best part. And we're going to just learn by example instead of making a general form of this. I want f of x to equal 2x to the 4th plus 3x squared minus 5. And I want us to take the derivative of that. So, finally. Oh, that was killing me. Okay. So, I know how to do this, and I know how to do that, and I even know how to just do the 5 because that's just a constant. But the question is, can I do them all separately and just leave the add and subtract in there? You guys, I know you're hoping the answer is yes, and it absolutely is yes. We can take the derivative of each of these separately, just leaving the operations between them. This is the best news, guys. So when I take the derivative, I can go term by term. Now, it's because these are added or subtracted. If this was different, like if these were multiplied in some way or there were parentheses, I would have to take other measures. But you guys, just adding and subtracting terms, just keep that same order in your derivative. So it means I can start with this term. So let's take the derivative. Remember, this is a coefficient, so it comes down. So I have 2 times this 4 that also comes down, power comes down. And then this x is now going to be cubed. See, guys, I got my first one covered. Let's go to the next one. There's a plus in between, so my derivative will also have that. Let's take the derivative of 3x squared. So the 3 is going to come down with. This 2 is going to come out in front also. And the power is going to go down 1, so this will just be x to the first. What happens to the minus 5 when I take the derivative? Is this a coefficient on x? It's not. This is a perfect example of a constant part of the function. So what's the derivative of a constant? It's going to absolutely go away. So this minus 5 is going to come down as, I guess you could say, minus 0, but it really does just go away. And if you think about that, it should make a little bit of sense. Think about taking the derivative. You go from a 4th power to cubed. You go from cubed to squared. You go from squared to the 1st power. You'll see in a minute that you go from the 1st power to a constant. What's the next? Once you're down to a constant, how much can you take off from there, you guys? You go from a constant to nothing. So anytime you just have a constant number in your function, it will disappear, basically. So let's simplify this a little bit. So this 2 times 4, we get 8x cubed, plus the 3 times 2 is 6, and that's just x to the first, so I'll just say 6x. And this minus 0, I'm not even gonna write that. So you guys, this is the derivative of that. So just going term by term using the power rule, coefficients, or constant rules. Let's talk about this one. You guys, sometimes you're just going to see x by itself, or maybe it has a coefficient. And even though it's really not different, you still use the power rule here. It's a little harder to think about because we're not always up on what certain exponents mean. So if I just have an x, remember there is a 1 here. You guys, this is x to the first. So using the power rule, when I take the derivative of this, what happens? This 1 comes down in front. And I have to take a power off, you guys. So if it's already at a 1, if you take 1 off, it becomes 0, right? And this is what gets us sometimes, is what is x to the 0 power? So it's 1. You guys, x to the 0 equals 1. Anything to the 0 power equals 1, not just x. It could be anything you want. If you raise something to the 0 power, it equals 1. So when I'm reading this 1 times x to the 0, it's really just 1 times 1. And you just get a constant. So let's do another one, just like this, because I want you to get used to plain x terms, x to the first terms. Realizing that all that's going to happen is they're going to turn into a constant. And again, that should make sense. If you only have 1 power or 1 degree to take away, you take it away and now you're just at a constant value. So the derivative of x is 1. Let's put a coefficient on it just to make sure we understand what's happening here. The derivative of 5x. Let's use the rule. This is a coefficient, so it comes down. Remember, this is x to the first here, so this 1 comes down in front, and I take a power away, and I get 5 times 1 x to the 0. What was x to the 0? It's just 1, right? So it's 5, guys. It's just 5. And you guys, I don't want you to have to use the power rule on this all the time. If you have 5x, take the x off. Here's the derivative. If you have 1x, take the x off. Here's the derivative. So it really is like you can just disappear the x. And you will get used to that, and it'll become second nature. But sometimes when we're just learning, we're trying to do the power rule like step by step on every problem. This can trip us up a little bit. Okay, so I'm trying to think if there's any techniques. There's tons of techniques. We're going to learn so many techniques, but this particular chapter or section 11.5 covers power, covers coefficient, covers constant, and that's really it. So I am going to stop there for the day. And guys, like I said, 11.4 is up, and I mean, when you look at it, you're just going to want to take these short derivatives and do that. That's great. Just make sure you know that if I do ask for you to use the long way on a problem, like on a test where you show your work, that you're going to have to do that. So it wouldn't be a bad thing if you practiced on 11.4 with those. I'll also be putting up 11.5, and absolutely you have free reign to use whatever shortcut you want starting in 11.5. They should be pretty easy because these rules are really easy to get used to. You will be able to do it in your sleep, you know, in a week or so. So that's it for today. So go check out 11.4. I will be putting 11.5 up. It'll be on later today. And that'll all be due on this coming Sunday. So, okay, I'm going to end it then. And I will see you guys here, same time, same place on Wednesday.